Okay, I'm just going to check if the sound is working properly. There should be no mishaps unlike last time. All right, everything seems fine. All right, it's 11. Let me get started on time this time. And I'm Alex Shim, and I am working with Data Cabinet, and we are creating a platform, well, which is um, which is creating opportunities for individuals and also for businesses as well to basically to sort of streamline the process of designing and creating models and making it more accessible. Um, and today we're going to be covering generative adversarial networks for image classification, and they are well, in this case, they are a deep learning framework of sort of like autoencoders, where the idea is that you can, well, I guess I'll get to that in a bit, but it's a way of creating images and generating false images through a sort of a through a a game. And hold on a second, I may have a question or a side issue. Um, Hello, can people hear me? Maybe my volume is too low. Let me check this. Okay, let's try that again. Let me ask in chat if people can hear me. All right, okay, I increased the volume a little, so that should be fine. And so we prepared a few things so you could tag along with us. And one of the things that we did, and we actually prepared a project environment based off the Stanford Computer Vision Labs CS2 image recognition courses um, framework. And it has, so if you import the project, you'll be able to, it's sort of a tie into the GAN framework because actually some of them they have certain notebooks as well for designing GANs, and I happen to sort of piggyback off those. And in actuality, it's a lot more flexible than that because you can pretty much it provides you with enough tools that you can design like convolutional neural networks or current neural networks. So it's very flexible, and you don't have to install any dependencies. You just import it, and then you can just start coding or whatever you want. Um, and unfortunately, I have a, okay, all right. So let me continue. So I highly recommend that you try to import the project yourself. I think you'll have to register with Data Cabinet and create the account. And if you, hopefully you've already done so, but if not, you can just start importing it. And if you have any technical difficulties, then you can reply in chat and people will help you out. And it'll take a couple of minutes to set up, but then once you can do that, you can sort of play around with it during the talk or like on your own free time. Um, but anyway, with that out of the way, I wanted to go over a brief overview of what we'll be covering today. First, I'll start off with some interesting examples of GANs, and um, including some of the most state-of-the-art examples, which have very impressive results in terms of image generation. And then we'll sort of talk about the basic GAN concepts briefly, and then we'll then we'll mention some of the applications of GANs, like such as, I mean, we think about them in terms of image or just sort of mostly it's used to generate images, but then you can also use it to generate languages, or there's something called conditional GANs, where and you can also fill in information. So just the very nature of GANs, it's sort of, I mean, since it's creating images and creating data, you can sort of fill in data from like sort of simple data, and you can also think of it in terms of like if you could have a lot of um, you could have supervised data and unsupervised data. So you got labeled data and unlabeled data, and can actually learn a lot from the unlabeled data, and you could have a smaller amount of supervised data, and it can sort of learn to sort of fill in the labels on its own, sort of combining the knowledge of the unsupervised learning as well. And then we're going to talk about sort of the issues with training GANs. I mean, we're talking about how successful they are. We have all these great examples, but there's actually a lot of problems and challenges in terms of their stability. And we will talk about those. And I actually created a notebook which is going to illustrate from a very simple example why these what is actually happening and why these occur, and sort of inspire some ideas of working around them. And then we're going to go through um, the creation. Once we know all these things, it'll actually be a very straightforward procedure to create our own GAN, and we'll be doing that in a notebook. And then we'll discuss some stabilization tricks, some of which are pretty obvious once you've thought about these issues, and some but overall a bunch which were mentioned by, I think, in a NIPS GAN conference, I think a year or two ago. And then we're going to go on to some of the more esoteric advanced architectures. Um, and finally, um, we'll finish with talking about the how to like sort of the architecture of the progressive GAN, which is the most state-of-the-art one. And speaking of which, we're going to actually show some of the results. So the progressive GAN authors, they made a video of what they could accomplish. So I'm just going to show this video, and hopefully it'll play pretty well. Actually, let me blow this up a little. How do I make it bigger? Okay, that was worse. Okay, sorry. Um, so here, what it's doing is it was trained out a bunch of celebrity image faces, and what it's actually doing, it's morphing between one celebrity image to another celebrity image, and actually all these images in between are created using GANs, and just by the nature of GANs, they have some sort of continuous. They're mapping this latent representation into the space of images. So it's actually able to transform, um, it's sort of able to bridge, like create realistic bridges of images in between different types of images. And so as you can see here, it's morphing from like very different looking people, like female celebrities to male celebrities, sometimes of different races, different skin tones, different hair colors, different expressions, but it's actually morphing between them very smoothly. And it's a pretty impressive result because well, first of all, that it can do that sort of interpolation, but also that all these images are extremely realistic. And if you actually look at examples for autoencoders and other computer graphics image generation, then a lot of them do not look very realistic at all. So it's actually quite a difference. In here, I want to show they provided another example where they did the same thing, but for a different class of categories instead of faces. Um, so here, so at the bottom, they're mentioning there's birds, boats, bottles, and planes, bridges, and different classes. And it's in same like with the celebrity faces. It's morphing between like different types of cars on the middle right and different types of cats on the right hand side. Um, and so overall, very interesting, very extremely realistic images. These are all like basically fake images, but it's sort of doing this continuous transformation between all of them, and it's actually really amazing. Um, like because we would think that, well, we know what's a real image and what's not a real image, but it's actually sort of learning to represent what we think is a realistic image. Um, so I'll play that a little more, and then I just want to see if there's any questions. Okay. All right. Okay, so let me move on. So usually I have multiple screens, so this is a little, but in this case I only have one monitor, so it's kind of hard to uh, monitor the chat and also look at my own screen at the same time, so I apologize about that. Shoot. Okay, no, that is the incorrect window. All right. So let me move on. All right. So, and I wanted to, so that's sort of more some of the state of the art. Oh yeah, sorry. The next slide is something called StarGAN, and this is also demonstrating this sort of transformation capability. And the interesting here is that you have all these inputs. These input columns are actual celebrity faces. But what the GAN has learned to do, or what StarGAN has learned to do, is that so it has this sort of latent space of it has this latent space of variables which mean absolutely nothing, but it learns to map those to input. So over here, what it's learned to do is it's learned to assign certain dimensions of the space to something like what color your hair is, or are you male or female, or what's your skin tone, or how old you are. And actually, by what it's doing is that it can actually slide the value of like the age dimension or the gender, and so you could take some sort of image input which is a male, but then you can actually change the gender by like changing the sort of like gender dimension by a certain amount. And you can do the same thing like with blonde hair. And on the right side, they're doing the same thing with expressions. They're taking a face, or I guess a celebrity face, and then they have, maybe there is some dimension for how angry somebody is, or there's maybe, or more accurately, there's an area in the latent space which sort of represents like things that look angry or things that look happy. And by moving in that general direction, then you can make somebody who's not angry at all, like, and change it so they look pretty much the same, but they start to look angry, or they start to look fearful. So it's learning this sort of it's this latent space. It's learning this representation of different features, and it can like smoothly push it more and more in that direction. There's a famous picture, or there's a well, famous for deep learning examples. There's a famous picture where they took a celebrity and they learned what eyeglasses looks like, and they sort of interpose like glasses onto somebody without any with no eyewear at all. And it's pretty interesting. And it'll make more sense when we go through the concepts a little bit. Although my focus isn't going to be on the theory so much as, I guess, trying to actually construct it ourselves. So those were some really good, like high quality examples. I'm also going to mention some older examples of GANs, which sort of showcase what they can accomplish. So here, I believe this is a paper called like image-to-image translations. And what they're doing is, so for example, if you take this Google Street View, you might have this, you might take this very undetailed representation, but then the GAN can learn to like realistically fill in the this picture with like realistic like car textures and road textures. So you're turning something very simple, like like the building on the right, or this black and white photo, and you can do things like add color to it, or on the bottom right you have a handbag, and it's just like sort of a hand drawn picture of a handbag, but you can actually change that into this into an actual detailed picture of a purse or a handbag. And I sort of like to think about it as, well, what if you have, well, people will ask me if I'm talking to somebody and they're asking me, well, I'm trying to mention, oh yeah, do you remember that person? And then I'll try to describe some features, like, oh yeah, uh, he has black hair and he's this tall and he's like this race. And usually I don't really provide enough information to sort of describe them well enough to accurately depict them. But when you think about it, there are police sketch artists where they learned, they're taking these descriptions where they're like, oh, there's a suspect, can you describe the suspect? And they try to draw this portrait of them. And when you think about it, they're providing like sort of these some details, not too many details, but these sort of sparse details. But then they're generating this like actual, like, or hopefully semi realistic, like almost photograph of what that suspect actually would look like from just their descriptions. And they might say, oh no, their like eyebrows are a little higher, or whatever. But they're doing this sort of image generation process, but they're doing this from like a very so you could think of it as mapping these lower dimensional inputs, which would be your sort of verbal descriptions, to some sort of like actual detailed image. And they're not like, and at the same time, they're actually going to create realistic pictures. They're not going to create like, you describe a person and then they draw an alligator instead. So this is showcasing that you can use it to sort of fill in information or transform it and add or remove information in certain ways, but also in a very realistic way as well. And another example is that you can actually use, and this is a little bit harder, you need to use some sort of some reinforcement learning concepts to do this properly, but you can also do language generations as well. And this can be useful when you need to, I guess in translations, one of the issues for translations is that translations don't map exactly. Like there are multiple ways to translate like a sentence, especially a longer sentence, and none of them are completely wrong. So in some ways, the normal way of doing translations it's somewhat limited, because if you have one input and one output, but there's actually a lot more flexibility in between. So if you want sort of to make your to sort of expand your data set, maybe you need to like generate somewhat realistic translations in order to like have more flexibility for your translation model. So in order to do that, you need to have some sort of it will be helpful to have some sort of language generation, and GANs can do that as well, although it's a little bit different because images are pretty continuous, because you can think of there as pixel values, for at least for computer images. But for language, words are discrete, so it's a little trickier to do. But so in this example, they used something called the Wasserstein GAN, which we'll describe later. And generate, well, it's sort of gibberish, but it's actually like it's kind of realistic looking words. There's no semantics behind it, but it looks. But if you're not paying a lot of attention, you look from further away, it kind of looks like a real. It doesn't look like like it's just complete gibberish. Well, it looks like somebody may have actually written it. So it's pretty interesting. And of course, GANs are still a work in progress, even though they have like pretty impressive results. But there's still a lot of challenges, which we'll talk about a little bit later. So I guess. So one of the things we should start out with is, and we sort of hinted at these or mentioned these while we're talking about examples, is what is a generative adversarial network? And the simplest question is, what is generative modeling? And so we mentioned before on the bottom that one is that we could create samples. So if we have, we could create artificial images and create like realistic images. So assuming you have reasonable data, you can create more. You can create more data which sort of simulates, and your model is going to represent what those images would be. And in the line above, it's talking about density estimation, and this is the more mathematical way of thinking about generative adversarial networks. It's that you have your empirical data distribution, which is like, but you don't know exactly what this distribution is. You just have a lot of samples. And it's hard to say. I mean, you can represent an image as like pixel by pixel. Each pixel is a dimension, and you could there's 3 color channels like red, green, and blue, and you could a 1024 by 1024 pixel picture would be like a 3 million dimensional input. And of course, there's way too many there's too many dimensions to actually work with. So you can't. So at some point, it's unreasonable to say, well, what is the realistic picture? What is a set of realistic pictures, or the manifold of realistic pictures? That's too hard to describe. But you can sort of implicitly do this by doing this. If you have a generative adversarial network, we can sort of create the data. You can sort of a generator network which creates a probability distribution or creates samples from the probability distribution. And there's, well, I guess I don't have a slide for it, but there's the general, one of the motivations behind generative adversarial networks, or GANs, I'll just say GANs for now. One of the motivations was that it turns out so for a lot of our highly successful image recognition models, if you add just a little bit of noise to the model, you can completely change the classification. And the way you can think about this is that you could sort of have the set or the manifold of dog pictures. You could have the manifold of cat pictures. And if you draw roughly a line from a dog picture to the set of cat pictures, at some point it's going to switch classifications from a dog to a cat. And it turns out you don't actually have to move that far. You only have to add a little bit of noise, and it's going to cross this like decision boundary. So Ian Goodfellow, he worked at Google, and then he worked at OpenAI, and then I think he's back at Google again. He invented these generative GANs, and sort of, and this sort of problem was this problem of adversarial examples was sort of like the motivating factor for him. It was that you can easily fool like all your image models. So the motivation was, well, what if you use the idea that so if you could create bad examples or fake examples which could fool things, maybe you could specifically use those, train on those examples in order to improve your model. And the way Goodfellow describes it is it's sort of this contest between it's sort of this game between two parties. And his example is between counterfeiters and police. So the objective is to create money. So you have like real money, and the counterfeiters start to try to create fake money, or they try to counterfeit money. And so early on, the counterfeiters aren't very good. So the police can sort of tell, oh yeah, this is definitely counterfeit. So that they can easily classify like real money from counterfeit money. But eventually the counterfeiters will get good enough at generating this counterfeit money that the police are starting to get fooled by it. So at some point, the police have to become a little bit more, they have to become wiser, and they have to get a little bit better at discriminating between real examples and fake examples. And you'll notice that if you ever read about money, then they add in like certain little tricks, like there are certain numerical patterns, which there's certain number combinations, or and there's like hidden details in the money, and there's like little hidden strips and stuff like that, and like the color has to be a certain shade. And then so they're adding that so they can distinguish between real money and fake money better. But at the same time, the better the police get at that, then the better the counterfeiters get at, like they in order to beat the police, they have to get better and better as well. So it's sort of this game where the counterfeiters and the police, they have to work against each other, and in the process, both of them get better and better at what each of them do until eventually, or if you do this long enough, then hopefully you'll converge to something where you'll have like a perfect counterfeiter and you'll have a perfect policeman. And so Ian Goodfellow formulated GANs as this sort of game between a generator, which would be the counterfeiters, and this discriminator, which is the police. And he created this sort of feedback or loss function from whether the discriminator detected whether it was the example was fake or not. And so what we have in this slide is sort of a a description of what's actually happened. So on the left side, is what happens with real data, and on the right side, it's what happens with fake data. So on the left side, you just sample some input from the data. So you sample a picture, you pass it to your discriminator, and your discriminator, it's a deep learning network. So basically, I mean, it's just a function, and your discriminator processes your input, and then it outputs a probability if it's real or fake. So and the discriminator, it has to improve itself. So it needs to try to it wants to classify real images with a high probability. So that's one of its objectives. And on the right side, you have generated data. And the way they generate data is they start with just arbitrary latent space, so some n-dimensional space. And basically, you can think of it as just input noise. And you pass that into a generative function, and it's going to try to generate some realistic example from the generator is going to create a realistic example, and then that example is going to be passed to the discriminator like before. And this discriminator's objective, it wants to classify real images as real, and it wants to classify fake images as fake. So the discriminator's training is going to try to reduce the probability of fake examples. But at the same time, the generator, it has sort of the opposite goal. It's going to try to want to make the discriminator classify its fake images as real. So the generator is working on this G tries to make dg of z near 1, and the discriminator is working on this D tries to make dg of z near 0, and on the left side, D of x tries to be near 1. That's the basic description of it, and we'll actually go into a very simple example, which will make it pretty obvious. But I think first we're going to just briefly mention some other. We're not going to go into too much detail, but for Ian Goodfellas' basic deep learning model, he was just creating a very simple, like fully connected network. And it's just basically a linear model. You add a nonlinearity, and maybe you have a few layers of these. And if you know anything about convolutional networks, well, it turns out that convolutional networks are a lot better at working with images. So naturally, instead of just using a fully connected model, they just changed the generator and discriminator into using convolutional neural networks instead of fully connected networks. And that's the amazing invention they did. And it works a lot better, and it's actually something that's you can implement in one of the notebooks as well. So I mentioned supervised and semi-supervised data, and this picture sort of represents different approaches to using supervised data. So the basic GAN, it only classifies if an image is real or fake. But you can add a little bit of more information to that. You can say, well, let's say you have 10 different classes, like they could be types of animals, or they could be digits for MNIST. And what you can do is you can add in this extra information, or you can create like separate discriminator network, generator and discriminator networks for the conditional GAN, or you could add in these labels, or you could output whether real, fake, or the class. Or sorry, the discriminator could pass out two outputs. One is that if it's real or fake, and the other is, I guess, assuming it's real, what class it's going to be. And there are as you can see, there's a lot of different ways of doing this. So there's a lot of different architectures. We're not going to go into those that much, but the idea of using this class information in addition to just the basic adversarial setup, that provides a lot of useful information. And particularly, you might have, it's useful because sometimes you have a lot of unsupervised data. For example, I have a lot of pictures, but then it's a lot of work to actually label those pictures. So you can take a smaller amount of labeled pictures, and that actually can provide enough information for the condition part that the model can learn to. So the unsupervised part on the unlabeled pictures, your model can still learn like what's real or not, and they can sort of group things together and naturally on its own. And once you add these conditional labels, then it can learn to map like some of how it represents the pictures to let's say the classes as well. And so it can combine those together to efficiently use a small amount of supervised data and to create a lot of unsupervised data to make a model which can classify in unsupervised data with a lot less labels. And like what I mentioned before, for language modeling, for discrete outputs, then they're like for natural language, you're outputting word tokens as opposed to pixel values, so it doesn't work that well. And and usually for GANs, the generator has to be differentiable. And so in this case, if you're generating discrete word tokens, that's not differentiable. So you can't do normal gradient descent on it, and that's problematic. But the ways you can work around that is that you can reinforcement learning. It has to deal with these sort of discrete outputs as well, and so they've learned to do policy gradients, which works with discrete outputs. And there's other interesting methods of doing it. For example, I think they mentioned it was 2016, but I thought it was early 2017. But they sort of reinvented the concrete distribution, or the Gumbel softmax distribution, and they learned to sort of like create this sort of softened representation of discrete outputs, but then in a way that you could actually do calculate. But they softened it so it actually was differentiable, and they could do calculus on, or they could calculate gradients upon it. And let me. All right, so let me see if there's any questions, which I have not been paying enough attention to. Ooh, that's bad. Okay. Oops. Any questions? Okay. Adding noise. Oh, there are questions. Great. Okay. Adding noise and hoping then to another class, will this be a security issue we could create with GAN models, especially for things like recognition or others? I don't fully understand this question. Let's see. Adding noise and hoping then to another class. I don't understand what security issue means in this context. There is, I mean, when you think of things like CAPTCHA, where they're trying to recognize whether it's a human user or robotics user, then yeah, I mean, I don't know if that's your question, but if you have good enough generators, then you should be able to fool no matter, or if you have a good enough discriminator, then you should be able to determine if some sort of fake output is real or not. So you should be able to classify those things. Like if they're usually doing something like they have a bunch of digits, but then they add a whole bunch of noise, and that noise it fools most convolutional neural networks. But in theory, if you have a good enough discriminator, you should be able to distinguish that. Once we add noise to a class, and then we move to new class labels. Once we add noise to a class, then we move to new class labels. Will this be a security issue to fool the system with GAN models? I still don't completely understand. I'll think about it. We can maybe discuss it more sort of near the end. Okay. All right. Okay, so, oops. All right. So let's continue. So GANs, they sound wonderful. You can train things, you can create realistic images. Sometimes they don't work so well, and sometimes they behave. They start creating some. There's some problems in terms of the images that they generate, and we want to understand why this is happening and why it's so unstable in training. And we're actually going to. So I'm going to. Wonder what order would be best. I have a notebook which sort of demonstrates it, and at the same time I have some slides. But actually, let me start with the slides, and I'll briefly go over them. It may not make that much sense, but then once we go through the notebook, then it will make a lot more sense, and then we can just take a look at the slide again, and it should be super obvious. So there is something called mode collapse, and so let's not worry about these equations for now. It'll become really obvious when we go through the notebook. But so the actual GAN objective is that it's the right hand side. No, the left hand side. I think it's the left hand side. Yeah, it's the left hand side. Where you're first you maximize the outer loop. You maximize, or you're trying to minimize this loss function for the generator. So the generator is trying to fool it as much as possible, and on the inner loop, then it's trying to the discriminator is trying to do it the best it can to to classify things properly. And the problem is that when you train generative adversarial networks, it's that you are what you tend to do is you train the discriminator a bunch, and then you train the generator a bunch, and then you train the discriminator, and then you train the generator, and so on. And the problem is it's not when you alternate these processes, then it no longer becomes this. It's actually alternating between this sort of left-hand side objective and the right-hand side objective, and that's actually not what you want. So what you actually want is that if you completely understood max VG of D, like if you completely understood how the generator affects this inner loop, this max D VG of D, then you can just find the generator parameterization which does that, and you would do that in one shot. Of course, the problem is that you can't actually because we're doing iterative optimization, so we have to do it a little bit at a time. And if we train the discriminator, if we train the discriminator too much, it doesn't actually work that well. So what we're actually doing is that we alternate between like k steps of discriminator training and one step of generator training and so on. But then it creates this sort of mode collapse problem, which I'm going to explain in the notebook. But basically what actually ends up happening is that, I mean, so you want to classify, let's say, all these different dots, but what ends up happening is because it's doing this it's sort of doing this right-hand side optimization, it will actually fixate on a certain point which sort of helps it, which fools the discriminator the most. And then at some point the discriminator will learn, oh, okay, so we know that the generator is like sort of overcompensating by trying to cheat by focusing on this point. So we're going to actually lower the probability if it's on this point which the generator keeps choosing to fool us. We're going to assume that it's very likely to be, it's much more likely than usual to be false. So then the generator is going to figure out, okay, well, the discriminator is no longer being fooled by this point that I'm using. So now I'm going to switch to like the next most likely point. And then the same process will happen, and it's going to alternate between it's going to sort of switch, move between point after point after point. So this means it may not actually converge. All it's doing is sort of moving around. It's moving around all its probability mass for the generator to different areas. But what you want in the end is that you want this sort of like middle picture with all the dots where it properly distributes the point mass. But because of mode collapse, it'll actually at a certain point in training, it's going to collapse onto a certain area. Okay, and actually, let me go into the notebook itself, because the other two, they're not directly related. But so if you open the notebook, I might have to reload. Okay, if you open the notebook, I created a notebook called SimpleGAN. It is loading. It is loading. All right, so to interpret this, I mean, if we used images, it's sort of super complicated. So instead, what I'm going to do is simplify it into a much more obvious example. So I created a space of, so let's assume there's a space of 6 images, or the input as 6 possible inputs. And if it's one of these inputs, then there's no difference between any of them. And so the 6 classes, or the 6 types of input are, I mean, it's basically whales and tigers, and you have a blue tiger, an orange tiger, and a white tiger. And I can try to blow this up a little. Okay, a blue tiger, an orange tiger, and a white tiger. And then at the same time, I have a blue whale, an orange whale, and a white whale. Now, blue tigers do not actually exist, to my knowledge, so this is completely fake. So in the real world, this will have a probability of 0. Orange whales also do not exist, so they'll have a probability of 0. And orange tigers are very common. There are a couple of white tigers, but they're a lot less common than normal tigers. And there's a lot of blue whales, and there is far fewer white whales, although probably not as rare as the white tigers. So let's come up with a probability distribution for our data. And it's going from, well, I wanted to align this left to right, but it didn't end up happening. But basically, I create a probability distribution. So this this blue tiger, it's assigned probability of 0. I decided the whales were more common than tigers. I don't know if that's true or not, but I assigned it like 20% chance. 20% of our images are going to be orange tigers, and 5% of our images are going to be white tigers, and 65% of our images are going to be blue whales, 0 are orange whales, and 10% are white whales. And you can actually change these numbers however you feel like. It's not really that important, but you can play around with it, and that's so yeah. So we can, let me just sort of execute this real quickly. Okay. So so what GANs are doing is effectively, so what you want to do as a GAN is you're trying to sort of calculate, you have 2 probability distributions. You have the probability distribution of your generated data, and you have your probability distribution of your fake data, or of your real data. And you sort of want to compare the distance between these probability distributions. And the natural way that we do this in data science is that we calculate the KL divergence. And part of doing that is that you calculate this, and it's basically, I mean, I could type it out, but I don't have it offhand. But it's, the formula turns out to be like P log Q minus P log P, where P log P is an entropy term. And this P log Q, so P is one probability distribution, Q is another probability distribution, and this P log Q is a cross entropy term. So what we're going to be doing is that, so our probability distribution for our real data and our fake data, it's going to be p data times, it's going to be a joint probability distribution between between p data and our space of labels, which is 0 and 1, or real and fake. So there is a slight problem here, and that is that if it's going to come up a lot, and if we, to do this P log Q, we need to calculate the logarithm of P of let's say a probability distribution. And the problem is, if we take the logarithm of 0, it's actually negative infinity. And if we take the logarithm of 1, it's 1. And I made a little example of this. So it's going to give up these warnings because it doesn't like taking the log of 0. And we have a little graph of this, and using Matplotlib or Matplotlib. And yeah, so as the logarithm approaches 0, the logarithm is, or as the input goes to 0, then log of x goes to negative infinity. And this is really bad if this is one of your loss terms, because now you have like negative infinite loss, and it's just it's going to blow up your model. So it's not good. So let's keep that in mind. And so one of the things that we're going to have to do when we create our GANs is that we have to figure out our loss function, and our loss function is going to be based off of our cross entropy. So So let's start by creating two very simple discriminators. And I thought about, well, two very simple discriminators. I classify everything as fake, or I classify everything as real, and that's what I call D1. So here, this first row is going to be the probability. I split up the discriminator into sort of two columns. One of them, um, so the first column is a probability the input of type X. So like the left one is blue tigers and so on. So this is the probability that I will classify, my discriminator will classify it as fake. And the bottom one is it's the probability that I classified as real. And vice versa, I created D2. It's going to classify everything as fake. It's going to classify nothing as real. So I felt those are two really obvious discriminators. And so now we can start seeing how what's happening for our GAN. And so now let's figure out what cross-entry terms are most appropriate. And we're going to try various combinations. And so I mentioned above that we had this sort of log p data and it had negative infinity, and we don't like negative infinity, so we would rather avoid this. So it's pretty sensible that we want to keep the discriminator we don't want this p of data. Well, maybe we're going to try to keep p of data on the outside, and we're going to try to have the log of the discriminator, or log of the discriminator on the inside. Is that right? Well, it should be right. And yeah, that's right. Okay. And we want to, so the question is, we have to figure out which of these, we're going to try p of data times log of D1 of the first column, or the first row, and p of data times the log of the second column. And we're going to see what happens, and we're going to do the same thing with D1 or D2. So we calculate this here, and so what is this expression exactly? P of data times log of D of 1. And well, this is basically the same as P of data times I'm taking log of D1, but I'm multiplying all those by 0, because we're saying that for the actual real data distribution, all the actual examples, they will be classified as fake with 0 probability, and they'll be classified as real with a probability of 1. So this sort of it's kind of like this. So this term is actually sort of, if you think of this, if you think of that you're adding this term, which is 0 times log of d 0 times the log probability that the discriminator classifies as fake. This is basically the same as this. So this term here is kind of like the cross entropy between P of data with the label and D1. And I said it's like cross entropy because, well, first of all, D1 is not actually a probability distribution. It's just a given an input, then what is the probability? So you would actually have to do something like the actual probability distribution is P of data times D1. And actually, if you calculate this properly, and so when I was trying to like assure myself of the loss function, I realized that there's a sort of small issue here. They're actually ignoring this P of data term, and if you calculate it properly, then there's actually this extra entropy term, but it might get ignored once you assume the cross entropy as well. But anyway, so this actually is what we're going to want to use for our discriminator in because we can see that it's representing the cross entropy of P of data with a correct label and our discriminator. And so what exactly is our other term? Our other term is, well, first let's evaluate it. Actually, so let me just talk about this output really quickly. So we can see here that this, once we evaluate it, this is all 0. But that actually makes sense because everything is being classified as correct. So everything has a, D1 is always 1. So log of 1 is 0. So 0 times probability distribution is just going to be 0. So that makes perfect sense. Down here, now we have a problem. If we calculate it, if we multiply times the probability distribution times the sort of like the reverse labeling, where this is sort of, So this is what's effectively happening. It's P of data times 1 times the logarithm log of the log probability that the discriminator classifies as fake, and 0 times the log probability that's classified as real. So this is sort of the reverse labeling where it's sort of like the data distribution but everything is classified incorrectly and the correct discriminator. And this is not actually what we want, but more interestingly here, we can see that there's a problem. And first of all, we have these NaN terms and these negative infinity terms. And these NaN terms, it means that it's actually something like 0 times log 0. And that's actually not that bad because 0 times log 0, if you take the limit of it, it actually goes to 0. And also when you don't actually know P of data, you sample from the data distribution. So you end up just generating, you just end up not generating any data where P of data equals 0. So you just don't even see them at all. So this is the less important issue, and the negative infinity is a more important issue. And it's that for some of our D1 terms, actually, for these D1 terms, D1, we're calculating D1 of 0, or D1 of x, which is always 0. Is that right? Yeah, the probability that's being classified as fake is always 0. So we're taking some actual value like 0.2, and then we're multiplying it times log 0. And log 0 is negative infinity. So now our loss is like has a whole bunch of negative infinity terms. And that's not great for us. And we'll get back to that later. And similarly for our D2, our D2, it classifies everything as fake. And we can see here that if we calculate the proper P log D term, that you have the same issue as this sort of like reverse term for D1. You have this NaN term, which is 0 log 0, which is fine, but you have a whole bunch of negative infinity terms. So once you're taking, if the discriminator ever is 0 or has 0 probability, then you're going to have, if it ever assigns 0 probability to any of the images, to the real data images, then you're going to have like negative infinite loss, which is really bad. And we're going to discuss later how we can fix that. And similarly, we have this sort of reverse term as well here. And which is, of course, this is sort of the mirror image of P of data times log of D1. And so this is stable, this is not stable, because this is always log of 1, so that's fine, and this is always log of 0. Although this does bring up another point, that here, when we actually do training, if our gradients are always there's an issue in GANs where if your discriminator is too good, then your gradients will become when you take the gradient of the loss function, it might plateau and always be 0. So as you change the discriminator, or as you change the generator, it won't matter because your discriminator is too good. So your discriminator will always have like, the loss won't change at all. This matters for generator training. And that means that your generator will get stuck and will no longer improve at all. But anyway, so this is sort of hinting at these sort of like negative these infinite issues, which is going to cause like this sort of disturbing behavior and instability when we train our GANs. And so now the next step is like, let's try to create a generator. Now, how would we do that? And let's say I'm a person who has never seen whales or tigers. Then maybe the most intelligent thing, or one obvious solution, is I'm just going to have equal probabilities to all my classes. So I'm going to assign like 1/6 to each of these classes for our generator. And so now let's figure out. So before we had. So in this case, this is actually we're going to assume this is the outputted probability distribution. So before we had P of data, but now we have our generated data distribution, which I guess I should have called this P of G1, but I'll just call it G1. So I'm going to calculate G1 times log of D1 and try to interpret what that is, and G1 of times log of D1 of 0 and see what that is, and so on. And so G1 of log of D1 of 1. So this is d1 of 1 is the probabilities everything is the probabilities of being real, and d1 of 0 is the probability of being fake. So effectively, once again, this term is the same as 0 times the probability that the input is being classified as fake, and 1 times the probability that's being classified as real, which once again is like sort of this cross entropy of p generated times the label and our discriminators probability distribution. And similarly, and we can see here it's all 0, so that's fine. And over here, we could try this with d1 of 0 instead. And once again, this is effectively p gen times 1 times log of d1 fake plus 0 times log of d1 real. So once again, this is a cross entropy of p generated times with a label that all the fake images are being, all the fake images are 100% fake, and the real images have are being treated having a probability. So everything in this generated probability distribution, it's being classified. It has a label of 100 of being fake 100% of the time, and it's real 0% of the time, which is sort of what we want. So we can see that this term here is actually what we want for our generator term, or it's sort of the correct generator contribution. When our discriminator wants to sort of classify all our generated images as fake, we want to use this g1 times log d1 of 0. And the thing is, so when we actually do a discriminator, it's only going to output a probability distribution of being real. So this is actually going to be, this is actually 1 minus d1 of x. And we'll see that in the code for actual GANs. But once again, we see this problem. We have this sort of negative infinity. We have all these negative infinities because remember our discriminator is classifying everything as real. So that means, but that our generator is like they're all fake images. So that means our discriminator is like infinitely wrong for using KL divergence. So this is like huge error, and it's going to cause some problems. And we do the same thing for our discriminator, which classifies everything as fake. We could see that, yeah. So this second term it's the correct term, and we can see that. I think I had to run this. Let me do this. Run this. Run this. Oh, I forgot to define these. Run this. Run this. Anyway, so this is the term that we want. We have like these horrible negative infinity terms, and oops, we do this for the D2, and we do this for sorry. Yeah, so here, yeah, for this reverse type, we have this infinite problem again. And here we have this, it's stable again, but this is the term that we want. So we can see that the generator, if our discriminator classifies everything as fake, then our discriminator is going to classify all our fake images perfectly. Of course, it's going to classify all our real images completely incorrectly, but it's saying that there is 0 loss contributions from our discriminator that classifies everything as fake. What the hell is this? Okay. Anyway, so okay, so so this is bringing up bringing up the idea that first of all there are these negative infinite problems, and also it's bringing up. I wrote it this way because there's a trick that you can do with GANs. So you can see that some of these GAN losses are sort of mirror images with each other, and there's an actual GAN classification loss which I can bring up. But you can actually have this sort of like inverted version which accomplishes pretty much the same thing. So technically you're supposed to calculate something like log of 1 minus g, log of 1 minus g. But you can actually sort of like reverse the objective and accomplish the same thing. I don't think I'm being very clear about this, but let me, I'm going to move on for a bit because I want to talk about, I just want to show what happens when you actually train it. So let's say I do this sort of inner loop over here. So I'm maximizing the discriminator. And let's see what happens here. So first of all, the question is, what is the optimal discriminator? And well, assuming that we have equal amounts of real data and fake data, that means that if we have a perfect discriminator, what it's going to do is it's going to assign a probability. So we have so for a given input X, we have P-gen and we have P-generated and P-data. So our perfect discriminator should classify generated data with a ratio of P-gen over P of data plus P of gen. And it should classify our our data as real with P of data divided by P of data plus P of gen. So it should classify based off the proportion of the data. And remember, everything in this case, everything is identical. Although, well, I guess that point doesn't actually matter. But it's sort of the optimal discriminator. Once it learns properly, it's going to depend on the ratio of the data. And it turns out that actually does maximize the discriminator objective. Okay, so I created a function D3, which is the optimal discriminator. Okay, and we could see here that, I mean, this isn't that important. Well, yeah, so this is the blue whale, which doesn't really matter. Or sorry, this is the blue tiger. This is the orange whale. And of course, so since there are a lot more blue whales than any other class, and because the generator is it's generating fake data uniformly, we could say it's much more likely that blue whales are being classified as real. If we see a blue whale, since there's much more blue whale data than like fake blue whale data, it's going to classify as real more often than not. And in contrast, like the rare categories like white tigers and white whales, if we see a white whale, or if we see a white tiger, it's because our generator is going to overestimate the amount of generated white tigers. Our discriminator is going to classify it as fake most of the time. So over here, like 77% of the time, it'll think it's fake. And similarly with white whales. So that's sort of the optimal discriminator. And so now what happens? So let's say, okay, now we know what the optimal discriminator is. So now let's say we're trying to optimize the generator to maximize this loss. And the way we would do this is that we're going to sort of we have two separate terms. Actually, so I opened up the GAN notebook separately, and this is sort of the objective that we're doing. And so this E of log D of X, that's sort of the P data times log D. And this E of this E generated of P is the same as P generated times log of the probability that the discriminator classified as fake, which is 1 minus the probability that's being classified as real. Sorry. So if we move on, so where was I? Sorry. So I'm going to calculate the losses for both these objectives. So here, we can see that once again, we have this annoying NaN value, but that's not that important. And we have, this is our generated loss. And so our objective, so remember our discriminant, this is our discriminator objective, but our generator objective is to minimize this term. But under one assumption, there is no generator term for log D of X, which is not, there actually is for the optimal one, but for a given discriminator, then there is no G of term. So if we calculate it like the gradient of this, or something like the gradient of this, then we're going to ignore this for now because there's no generator terms. So all we have to worry about is this sort of this generated loss term, which is going to be P of generated times log of log probability that the discriminator classified as fake. Okay, so we evaluate this, and we can see here that, well, we have this generated loss, and the question is, how do we maximize this discriminate? How do we change this discriminator to minimize this loss the most? And we can see that the worst term here is this minus 0.26, and this represents the blue whales term. So this means that our discriminator is it's accumulating the most error for our blue whale category, which is actually also our most common category. So that means that if our generator, if we wanted to do it in this sort of iterative way, then our generator would want to, the way that it would increase, that it would improve the most, the generator would improve the most, it would just try to, because blue whales are misclassified the most, it should try to, it's going to like put all the probability mass onto blue whales, because that's going to lead to the most improvement. And so that's what it's doing here. So we create this generator. So it has a probability of 1 of being a blue whale, and everything else is 0. So if we remember this picture from before, this mode collapse, we've assigned it to like this sort of blue whale area. And okay, and now the question is, so now what happens? I'm going to move through this a little bit more quickly. So we create, so we have this new generator, and now we're going to find the optimal discriminator once again, like before, and it's just going to be, since we know P of data and now we know the P of gen, where you can calculate the optimal discriminator. Okay, we calculate it, and now we're going to look at the sort of this generator loss again. And so what happens here? So we've determined given our second generation of our generator, which is everything is a blue whale. Now we're going to calculate this loss for it, and we're going to try to maximize. We've calculated our optimal discriminator, and our optimal discriminator says, well, our optimal discriminator is deciding. So it's over here. It is that, well, because we know that there's a lot of fake blue whales, we're going to classify like only a 40% probability that any blue whale picture is real, and the rest of, and 40% of the, or 60% of the time we're going to classify as fake, and actually it's going to ignore all these other terms. So it's kind of assuming, I mean, I had to do this to prevent divide by zeros, but it will actually assign a probability of 1 that it will assume that anything which is not a blue whale is now like, well, it's probably real. So yeah, let me move forward a little bit. So, okay, so now we train the generator again, and what happens here? Okay, we look at this loss function, all right. And so now, so first of all, we get a bunch of NANs, because, I mean, it's just a bunch of zero probabilities of 0 log 0 terms, so that's not particularly useful. We see that this sort of blue whale term now is like, now it's like our worst term, because like if we saw a picture of an orange tiger, because our discriminator only cares about blue whales now, our discriminator is going to get fooled like 100% of the time by orange tigers and white tigers and white whales. So actually these three terms, this orange tiger and white tiger and white whales, these are going to create them, like if the generator wants to improve the most, it's actually going to start ignoring blue whales, because that actually has finite loss, and it's going to focus on this all the other classes, which is like orange tigers and so forth, because those actually have loss. Or in general, it's going to move once a discriminator gets too good at picking up on once the discriminator picks up on that single mode, then the generator is going to look for the next best option if the loss is finite. In this case, we have like this infinite loss, so it's going to sort of probably, I guess, do this proportion them equally. So now it's going to assign it's going to assign 0 probability to blue whales, but then all the other actual classes, it's going to assign probabilities to them, and we can do the same thing over and over again. But but we can see here is what ended up happening is that our generator completely ignored blue whales, and now our fake blue whales will have, sorry. So now our generator is, our next generator, the next generator is going to only do orange tigers and white whales and white tigers, and now it's completely ignored blue whales. So now the discriminator will go back again and it'll decide that, oh, there are no actual fake blue whales. So now like blue whales are, so our generator will generate no more blue whales, and then our discriminator will get fooled again, and then our generator will decide, well, I should have, because blue whales are like the best way of improving the loss again, I'll go back to blue whales. So then you have these weird little annoying cycles. And I think I took too long to explain this, but let me move on to the, okay, so people got this, but yeah, so maybe it might have been overly long, but I feel this sort of this explains this sort of weird instability very well. That like you could see that as we had a very simple example for a GAN, and we did this sort of non-gradient type optimization, but we optimized it, and then we could see that on the right-hand side, because if we actually optimize the generator, and then we optimize the discriminator around that, then what happened is it just collapsed to like the certain mode, which the generator just found the area which improved, which fooled the discriminator the most, and then you just calculated the optimal distribution around that. So it collapsed to a mode, and then it just like then the discriminator will stop getting fooled, and it'll switch around. And these are some more examples of that. Oh my God, it's taking longer than I thought. So here are a few more examples of, there are a few other problems with classic problems with GANs, and one is that, so yes, you sort of generate realistic textures, but at the same time, sometimes you get like some weird, it looks a little strange. And one is that it tends not to deal with perspective very well. So you get these sort of very flattened looking images, like these do not look three-dimensional. It's like it's a bearskin dog or something like that, or like it's a, and also there's a problem with counting, that maybe it picks up on the concept that, okay, dogs have eyes or ears or something like that, but it's just trying to see if there are eyes or not. And if there's multiple eyes, it doesn't really care. So you generate like these sort of mutant versions of animals with like multiple features and with the wrong number of counts. So there is a talk on how you can make GANs to work, and I'm not going to go through all of these, but I'm going to tie this back into sort of the notebook that we covered. And so the idea is that, well, what were some of the problems? One was that one is that sometimes we had vanishing gradients, which I briefly sort of mentioned. And so there's this common trick that we flip the labels. So there's this sort of min-max term, where we're calculating, we're doing gradient descent to minimize log 1 minus d of g of z. But actually, if the discriminator is too good, this tends to saturate and you just get gradients of 0. So there's sort of an equivalent formulation where instead of minimizing this, we could just reverse this objective. So now, instead of minimizing this, we're just going to maximize this. And it's effectively, well, they say it's effectively the same. It's actually effectively the same, but except for an entropy term. I went out and calculated this because I was a little bit skeptical. But, well, ignoring that, you can do this objective the same. And the nice thing is that instead of having 0 gradients all the time, which is really bad because you'll never improve, you'll actually have you'll have non-zero gradients, so you'll start improving again. So this trick is particularly useful. The discriminator remains the same as before. Normalizing the inputs helps, and this ties into this. And actually, this is sort of a more general idea of like, which normalizing the input also, they have similar ideas about batch normalization as well. And it's basically if your inputs if your values are uneven, or if they get too high, then it might cause more unstable behavior. I don't think that's a great explanation, but um, I feel it's this normalization. It's related to having batch norm on the generated input and the real input as well, because it sort of controls the input in a reasonable way. So here they mentioned. So this is all from a talk by, I think, one of the Facebook AI people. Okay, I thought I had a link somewhere. Maybe it's in the notes. But one is that normally in GANs they use uniform distributions. Here they mentioned they found it was better, although I don't see this all the time, so I'm not sure. I don't know if you should always adopt this, but they tried sampling from a Gaussian distribution. But also that if you're using a Gaussian distribution, you sort of have these spherical coordinates. So when you're running these interpolations, so normally we talk about like when we're doing interpolations, we're sort of um, we're thinking about this like glasses vector or angry face vector, or angry face line between like neutral and an angry face. And we're drawing a line between them. So, but if you have this sort of Gaussian distribution, instead of drawing a straight line, you sort of assume that you have spherical geometry, and then you move along this sort of like if you were to fit a sphere centered around the origin between these two, sort of with these 2 points, then you draw like the great circle in between them. Although I've never used that myself, but it's fairly interesting. So spherical gradients, this is actually sort of related to this modified loss function. So remember, if one of our instabilities is that we have our gradients are 0, and then we no longer improve. So, I mean, so there are a lot of tricks which are designed to try to avoid having these sparse gradients. And one is that, um, so for ReLUs or rectified linear units, it's basically if it's less than 0, then it just maps to 0, and if it's greater than 0, it's just the identity function. But the problem is that means if it's below 0, it has the gradient is just 0 all the time, and that's not helpful because it sort of saturates. And we want to have some small amount of signal. So what they do instead is they have something called leaky ReLUs, which is, and it's really simple. Instead of being 0, we're going to have like a slight slope to the curve. And it's very easy to implement. All you're doing is you just do the maximum of alpha x times x, where alpha is some small constant. I think there's a example here. So yeah, how do you implement leaky ReLUs? You just do a maximum function between x and alpha x, and you choose alpha as some parameter. Very simple. But it will provide some gradient as opposed to 0 gradient, which is what usually happens. And also, in max pooling, it's sort of doesn't have a great behavior. So Ian Goodfellow, he always talks about max out instead. So it's some sort of well, actually, I can't comment too much on that, but I know that he has all these very GAN specific tricks, which you don't actually see that much in other deep learning areas. But for GANs, I guess the instability problems are very significant. So having like these special nonlinearity functions and such to avoid sparse gradients, it's super important for them. So 6, using soft and noisy labels. And you don't have to remember all these, but you can just think back to what were these issues that we saw when we just did this sort of like simple GAN toy example. And one was that, well, we had this problem where we took the log of 0 and we got negative infinity for our losses. That's really bad because like it sort of greatly distorts our results, and it causes like our modes to like sort of it concentrates our loss into one area, because one loss is going to be infinitely bad. If there's an infinitely bad loss contribution, we're just going to like pile up all our generator mass around that point. So one way that you can fix this is that you can sort of smooth the label so it's not quite as drastic. So what they do instead is that once you're close to 1, you can just replace it with a random number which is almost 1, and if it's close to 0, you make it slightly larger than 0. And they call that label smoothing. And Yeah, and there's some noisy version. DCGAN, that's just the convolutional version of GANs. There are a few RL tricks where, so normally you're going to generate new generated images, but if you do reinforcement learning, and actually I mentioned this in some of my reinforcement learning events, that one thing that they do for sample efficiency is they keep sort of a history of they keep a buffer of past generated samples, and they sort of reuse those instead of like having, and this saves time from having to um, create everything fresh, and also it leads to a bit more stable behavior because we remember that remember our generated data when we had like that sort of extreme oscillating behavior of only blue whales versus never blue whales. I mean, that's sort of not good. So what if you actually sort of average it out instead, you might have a much more reasonable distribution. Um, and that will make it a lot more stable. And of course, this works well for policy gradients. Use atom optimizer, sure. I mean, but they do that for all deep learning these days. So um, one wonders why this is the case sometimes, but yeah, so that's pretty straightforward. I originally was going to, if I had more time, I would have separated these into like just sort of obvious stuff that like just or just good practice to use in general, and then maybe things that had to do with saturating, um, um, things that had to do with like these sort of going to negative infinity and then avoiding gradients of zero. Um, and there's some more technical ones like um, sort of better diagnostics. Like if you're instead of just so the problem is that uh, sometimes the only way to tell if a GAN's not working is that you train it for a while and then you look at the pictures. Basically, it means that your loss function is not accurate enough for you to assess whether it's behaving properly, because it might be sort of trying to solve it, but it's actually exhibiting some weird behavior. And so, if the discriminator loss goes to zero, then this is not good. If the gradients are like way too large, and things are then there's some sort of problem. And this is also true in deep learning. When you do deep learning optimization, you're supposed to like take the ratio of like the inputs with I think with the size of the gradients. I think it's supposed to be like 100 to 1 or something like that. Um, yeah, when things are working, there should be low variance for the discriminator loss. If it's oscillating a lot, then that means it's probably sort of like doing this switching between modes. Um, and finally, if they mention here, if the generator steadily decreases, then it's supposed to be using noise to fool the discriminator. So it may not be, um, it may not, it's learning to fool the discriminator with random noise instead of actual good images. Um, and this one was pretty interesting, but I'll try to. I don't think I should talk about it too much longer for time's sake. But it's that like, so usually you have a k number of iterations of your discriminator. So you do gradient descent. You have like k steps of gradient descent on your discriminator, and one steps for your generator. And you might think, oh well, that's sort of arbitrary. What if we like had a more uh, empirical way of doing that? And he mentions that, well, they tried it, and it's actually if they try to like have some sort of criteria, then it actually sometimes it makes it a lot worse, and uh, it's hard, and it doesn't behave as well as it should. Um, oops. And here, if you have labels, like basically you can do conditional GANs, and this will provide a lot more information. And also they mention using batch statistics as well, and adding that to GANs. Um, and that actually helps a lot, and because you're giving it more information, so it could distinguish between samples a lot better. You can train the discriminator more, add noise, blah blah blah, batch discrimination, discrete variable conditional GANs once again, dropout, et cetera, et cetera. Yeah, I didn't want to go through this too much, but it's more like I wanted more to relate those more to the problems that we saw for training them, and to just think of, well, what are the obvious solutions? Well, one is like, don't let your losses be negative infinity, or don't let your gradient saturate to zero, or just um, try to make sure that you don't have mode collapse, or make sure your discriminator is like training a reasonable amount of time. Um, so let me, um, Yeah, so there are more advanced versions, but I actually wanted to get into the, well, I wanted to sort of, I felt that once we got to this point, we would have enough knowledge to actually like train a GAN properly or code a GAN properly. And I'm going to check very quickly to see if there are any questions. Sure, okay, there are no questions, and I'm going to move on to actually how to code again. And I wanted to go through the simple version first because I thought it would, when you're trying to create a lots function, I feel now we have enough information to know how to do it very easily. Um, so, so this is actually, once again, this is actually from Stanford's course material, where it's sort of a notebook based off of training GANs, and it's very straightforward. And of course, what you're doing here is that you have your just basic setup. This is just for like visualization, da da da. You don't have to worry about it. Um, GPU. Okay. Well, this is TensorFlow stuff. Showing examples. Okay. So actually, I'm going to run this all so we can scroll through it while it's running. Okay. To be efficient with our time. So yeah, so I mentioned, so you have to implement a nonlinearity, the leaky ReLU, but that's easy. It's just instead of zero, a normal ReLU is just 0 and x. This is alpha x, where alpha is very small, and x. So very simple. Basic test for it. Oh wow, okay, it worked. Whatever. Um, so now we have to create some sort of sample noise. So this is basically our latent variable z. We're calculating. So our generator is g of z, where z is your random noise, or your latent variable. And how do you do that? Well, that's very easy. For the uniform case, there is a function you can just create. Basically, this is sort of an initialization. There's a random uniform function, and you want to do it for whatever the dimensions. I mean, you specify some dimensions for your noise, and then you specify the batch size. So it's going to be batch size by dimensions tensor. And then for random uniform distribution, you just specify the min value and the sort of interval, which is -1 to 1. I think you can do random normal as well, and you can specify the mean and standard deviation, but pretty straightforward. So this gives you a tensor of your noise for your input. Test it, whatever. Discriminator. Okay, so the discriminator, this is also very straightforward if you do TensorFlow. What we're doing is we're just creating a tensor with the appropriate shapes for your discriminator. We're just creating a 3-layer fully connected network, and we have weights. So it's just y equals mx plus b, or wx plus b for matrix multiplication. So weights times input, add bias, weight times input, add the bias. So um, this is just, so we define all these weights for the weights and biases, and then we just do matrix multiplication, we add the bias, and then we add our nonlinearity, which is our leaky ReLU. We do that for our first layer, we do that for our second layer, and for our third layer, we just do the matrix multiplication, and we return our logits, which we use for our softmax or our logistic regression. So once again, I mean, this is just mostly linear matrix multiplication with this added nonlinearity function, which is, I mean, if you get used to deep learning, it's very straightforward. This is just some sort of test to make sure the discriminator has the correct number of parameters. Generator, same thing. You're just going to create a 3-layer neural network using tf get variable and get variable. Yeah. Yep. We're just going to create a 3-layer fully connected network. And once again, it's just matrix multiplication plus biases. And I think they're adding a ReLU instead of a leaky ReLU there. And once again, at the very end, they're using tanh. Why use tanh? Because what we mentioned in the best practices for stability, we want our generator to output between -1 and 1, and the tanh function outputs between -1 and 1. and symmetrically too. So, okay, very straightforward generator. If yeah, you test that, and okay, and so now we define our GAN loss. In our GAN loss, the way to do this is that we want to remember we have P of data and P generated. So our P of data is represented by our empirical samples from our data distribution. So it's basically our data mini batch. And our generated data is just going to be, we take our noise samples and we pass them through our generator, and that's our generated samples. And remember that the actual distribution is going to be, the actual distribution is P generated times like sort of the labels. So if all the real labels will have, all the real labels will have probability of 0 of being fake and probability of 1 of being real, and all the generated labels will have probability of 1 of being fake and probability of 0 of being real. So here there's a TensorFlow has a cross entropy function, so sigmoid cross entropy with logits. So all you have to do is you feed in like the correct the appropriate labels, and then you feed in the logits, which we get from the discriminator. It's actually because in this version, like, or the discriminator, it's not actually calculating the probability, it's calculating the logits instead. But that's fine because TensorFlow can handle it. I mean, it has a function for it specifically. And so yeah, so this is equivalent to yeah. So this discriminator loss, it's like p gen times log of p of d of x, and that's this term, the real labels plus cross entropy with like the fake labels. I mean, so same as before. And the generator loss is just we're just maximizing log p. We're just doing this reverse we're reversing the instead of a minimization, we're calculating a we're maximizing the state. We are reversing this loss from 1 minus d of g of z to d of gz, and then we're calculating the max. And so, like before, we're just going to use our cross entropy function. And this sort of goes back to, and if you're not sure which one's which, then you can sort of go back to like the sort of simple GAN example and just sort of like play around with it until like you feel comfortable with which one is which. And then, so once we've done that, then we can test our GAN loss and to make sure that it's reasonable. And yeah, so here we tested it and our losses are, this is provided Stanford code for just testing it, because just more for troubleshooting purposes. So now for optimization, it sounds hard, but it really isn't. All you have to do is, like TensorFlow, you just call the atom optimizer function. You specify a learning rate, you specify a beta for the momentum term, and then I think you're supposed to add. Usually, you specify what tensors you're operating on, but I guess they're not they don't have it here. Oh, anyway, so they have a version of the atom optimizer for the discriminator and the generator, and and then all you have to do is evaluate the for TensorFlow. All you have to do is evaluate the optimizer, and you have to feed in the inputs properly. So here is just sort of the implementation for putting it all together. We have all our code for like specifying, for creating the latent variables, for creating the noise, calculating our generator, calculating our discriminator, calculating our optimizer, and calculating our logits. And yeah, so what we do, so this is just, sorry, get solver. So all right. So basically here, I mean, there's a faster way to do it, but all we're doing here is we're doing sort of a session evaluation of this TensorFlow optimizer operation. And if you do that, then it's, I mean, you got this code. Okay, so this is sort of the training function. So I think most of this is pre-provided. I don't remember which ones you fill out, um, but the meat of this is that mostly what you have to do is you just have to create your generator, which is fairly straightforward, your discriminator, which is fairly straightforward. You have to specify your loss, which you have to think about a little bit, but once you've figured it out, then you can do that easily. Use Atom Optimizer, and then you just run the session to calculate the loss, and then you run the optimizer for the discriminator, and then you run the for a bunch of steps, and then you run the optimizer for the generator for a step. And then you repeat that until you train. Um, so so here they actually uh, here they trained this properly. They actually took the data. They trained it, and this is specifying. This is showing. They have code which is visualizing, like generating. This is generated examples of the data, and we can see that it improves over time. So early on, it's just noise because the generator is not very good. And then it's sort of it's every now and then at like every 50 iterations, it tells us what our discriminator loss is and what our generator loss is. We can see that slowly it improves over time until it becomes more and more distinguishable, and so on. Yeah, and after a while, we have like reasonably good results. So that's a basic architect. So that's basically how you create uh, again. I guess probably the details, which I didn't really mention that much. It's just it would just be, or it would just be having the training. I mean, this is the training loop um, for the discriminator and generator optimizer. Let's see. This is just saying every like 50 samples or whatever, then print show in examples, and then output the loss, like uh yeah, okay. So all in all, even though GANs are they're very fancy, it's actually not that hard to train at all. um Let me go and check for any feedback or any questions. And okay, so hopefully that's enough. I mean, that's sort of a good enough starting point where you can sort of play around with your own, create your own GANs. But I wanted to move on to some sort of I wanted to briefly mention some more complicated architectures, and then also some more advanced ones, or and also some more advanced examples, and actually how you would implement some of those. Which so like specifically how you would implement DC GAN, least squares GANs, and Wasserstein GANs. So some of the other architectures is that you can add in so this is an example of D2 GAN where you have uh, instead of one discriminator network, you'll have two discriminator networks, and this sort of if you, this is sort of a clever way of trying to add stability to training. The discriminator, well, there are some details, like the discriminator does not actually output a probability distribution. It outputs like a real positive scalar value. There's the bidirectional GAN before, which I can go back up to the top. So the bidirectional GAN, what it's actually doing, so remember that a normal GAN, you have a generator, but what the bidirectional GAN is, it's sort of an interesting idea, which was, I believe it was suggested by Goodfellas, but it's that, I mean, you can create a network to go from latent variables to fake variables, but we can also create another network which can take real data and try to map it back into the latent variables, and we can sort of train this with a loss function as well. It's sort of related to the idea of variational autoencoders because they have a similar idea. And okay, and I'm just going to mention, I think, three more things, or three more types of GANs, two of which will be very implementable. And it's that, so, and I think early in 2017, so one of the problems is that the GANs was using this sort of Kale divergence loss, which wasn't very efficient at all. Which had some problems, and there are some stability problems. So one thing is, well, what if we find other? I mean, effectively, what you're doing is you're finding the difference between two probability distributions between the um, um, between your discriminators probability distribution and like your sort of combined generator and fake data and generated data's joint combined probability distribution. Um, so one question is, well, why do we have to use Kale divergence? There are other ways, like why not just use some other ways of comparing two probability distributions? And that sort of motivates the ideas of using different loss functions. And it sounds fancy, but actually it's not too difficult to do, and it's fairly easy to implement. So normally you're doing this sort of for GANs, the generator, you're doing like this. I think it's just a maximum, but you're minimizing, or you're maximizing log d, and then you're maximizing log of 1 minus d g of z. But they just changed that log term to sort of like a Euclidean distance loss between. So this is sort of the Kale distance between 1 and d of x, but instead of that, they just said, well, what if we take the Euclidean distance, so like the square distance between the discriminator and the label of 1, and the generator and the label of 0. And they did that for both the discriminator and the generator. And actually, we can go back to this example here where we just implement this. And once again, it's not that hard. All we have to do is change the loss function from our sigmoid cross entropy to just squared loss. So you just take our discriminator and you just take the score minus 1 and square it. And the fake score minus 0, which is the same as fake score, and square it. And generator loss, you do the same thing. So you do that, and then you can basically all you have to do is change that line, change your loss line, and you can do the same thing. And we can see here that we have, I think, slightly better results here. I believe it trains a bit more stably. So once again, not very complicated. The other question is, well, what if you want to? So these are just before the examples were fully connected networks. Well, what if you want to do a convolutional network? I mean, then all you have to do is you just change, you modify the discriminator and generator architecture to a convolutional network. Pretty straightforward, like before. And they specify some recommendations, like 32 filters, so output of 35, like 5x5 relus, with a Lakey relu, 2x2 max pool, 5x5 with 64 filters and so forth. And you can create it like before. And I think you can also just use Keras as well, and you could probably do it a lot faster. Generator, you should also have I think you should have a similar structure if I remember. Anyway, if you do convolutional networks, it's pretty much the same thing. And the last part is, before I briefly mention progressive GANs, is this Wasserstein GAN, which is a bit more harder than the rest. But actually, if we want to skip forward to the result, then this is just a modified loss function. Instead of doing log d of x, we're just doing d of x. And instead of doing log 1 minus dg of z, we're just doing minus dg of z. So implementation, surprisingly simple. Theory behind it, a bit more complicated. Basically, this is just an alternative distance metric, a more flexible one called the Earth Movers distance, or the Wasserstein 1 distance. And the theory behind this is that you have two probability distributions and you're trying to find the distance between them. And how do you do that? So what they're doing here is they're trying to find, you take the joint distribution between the one probability distribution times the other probability distribution, and you're trying to figure out the best way of assigning weight within that joint probability distribution. So normally it would be, if you assume they're independent, it would be like some sort of even uniform distribution. But instead what they're doing here is that they're modifying, there's some way of modifying how there are different ways of allocating weight in between. in the joint distribution, and they're just trying to find the sort of they're trying to find the configuration which minimizes this like norm which minimizes this norm distance. So kind of complicated in theory and also intractable, or something that you can't actually calculate. But there's actually a dual version where instead of thinking about it in terms of, instead of trying to find this directly, what they do is that they look at the dual problem where they just try to find, they think about the dual space on linear functionals. I don't actually, maybe not linear functionals, but on function space, and they constrain it to with certain conditions, which I believe here it's like a Lipschitz 1 condition, and so this is actually going to be an equivalent formulation. This expectation of f of x. So that this resolves to being, you're just finding a function which sort of does this allocation for you. So this is expectation of f of x for one probability distribution minus the expectation of f of x over the other probability distribution. And if you find the f which maximizes this, then this is equivalent to, this distance is equivalent to this distance. And so this neatly fits into the way we deal with GANs, is because so our maximization just becomes about finding this function. And well, like before in our GANs, well, we were just maximizing over a discriminator. So now we're going to replace, instead of worrying about KL distance, we're just going to find we're just finding this function f of x just like before under this sort of Lipschitz constraint, but with this modified loss function. See over here, supremum. And yeah, so in the end result is that these are actually fundamentally very, very different discriminators. Like this is a probability distribution for being classified as real or not. This is just a real valued, this is just f of x. This is just a real valued function with a certain Lipschitz constraint, but effectively the training is pretty much the same thing. It's expectation of only without the log term. So it's expectation of d of x minus expectation of d of g of z. Yeah, so anyway, and in principle, so very complicated, but implementation, it's actually, they define a discriminator and generator again, but the Wasserstein GAN loss, all it is just this, where is it before? They're just taking the expectation of, the loss function is just the expectation of d of x minus the expectation of g of x, and yeah, here it is. So here g of losses, it's just the mean of the fake logits. It's not actually fake logits, but they shouldn't have called it that. Sorry. So here it's maximizing dg of z, and here they're just taking like the average over logits fake is just the dg of z, and logits, I think the signs are reversed here, but this is the average of logits real, or d of, this is expectation of d of x, and here is expectation minus expectation of dg of x, just like before. So yeah, you don't even have to do cross entropy. All you have to do is just average it. And yeah, so I guess the hard part is like doing this gradients part. But anyway, once you do that, you can just pass that, you calculate the loss and you pass it through Atom Optimizer like before, and then you train it like before. So the loss function, it's actually not that bad to deal with. And the nice thing about it is that the Wasserstein GAN, at least in theory, it's supposed to be a much more stable way of training because inherently it accounts for like the geometry of the space a lot better. And finally, and this has gone on for quite a while, but let me, okay, there are no other questions, so I'm going to continue on to the last part, which is the progressive GAN. And the progressive GAN is the latest it's a state-of-the-art version of GANs. And even though there are all these sort of fancy tricks and architectures, progressive GAN itself, it's actually not very complicated at all. It's just more the way they've sort of had a clever way of like creating a larger structure. And basically, they start with a very simple model, a very low-level convolution, and they train it. And early on, it's going to be really fuzzy because it's very coarse because they're not um, they're um, it's just a very coarse model, like 4x4, like 4x4 blocks, and they're going to slowly add more and more layers to it. And I think they add them with in a way that like with some sort of residual connections. But basically, they can as they train as they're training the GAN, they're they slow like as the training progresses, they add in like these more these higher resolution like pictures or model blocks, and eventually so this means that they capture the global structure earlier on. They get more and more of the fine details as you progress, so you don't like, as opposed to normal GANs where you might just like um, you're trying to like figure out the entire structure at once, and like you're trying to figure out the fine details as well as the big picture details at the same time. But this is like, but the progressive GAN, it just sort of does the big picture things and then like figures out how things should look, and then it slowly fills in the details. So it's a pretty simple concept. And in the end, then you get like these extremely realistic celebrity pictures. Um, and I won't go over this too much, but basically it's um, if you actually think about it a little bit more, the question is, how do you add in these blocks in a reasonable manner? Like, I mean, are you just going to keep the weights the same, or are you going to is it going to mess everything up? Won't you mess everything up if you just arbitrarily add like an additional layer? And the way they deal with this is that they use I think they sort of add a when they increase the resolution, they fade in the layers by, let's see, yeah, so they treat the layer, so during the transition, yeah, they treat the higher levels, the higher resolution ones, like a residual block, where you're sort of like directly adding in the input. So that way that there's this sort of like strong signal for the higher layers to the lower layers, so it won't completely ignore what's happening. Okay. Sorry, I got a call. Okay. Okay. So, I didn't talk about that. I didn't explain that too well, but the basic I didn't explain the residual connections that well, but there are a few other details for progressive GANs if you're interested, and I actually have a link with the GitHub. There's a GitHub version with TensorFlow code, although it requires a GPU um, for progressive GANs if you want to try it out yourself. And they have a few tricks in order to keep it stable, and one is that they add variation using mini batch standard deviations. So originally there's this idea of adding a mini batch layer to GANs. This is not for progressive GANs, but just for GANs in general, to sort of like to make it behave more properly. They sort of added statistical information about the mini batch in order to keep it, in order to make sure that like it generated samples in reasonable ways, and also that they weren't overly close together. They are spread out a reasonable amount. So progressive GANs, it does something similar, only it doesn't go quite so far. And so what they do is they calculate the standard deviation for each feature and for each spatial location. So in the mini batch. So and then they just average it. They average out all these features and spatial locations to a single value, and they get um, so they average out. um, over all the spatial locations and just the average value of the features or the standard deviation of the features, and they just sort of append that value to the mini batch. So each mini batch has this sort of like average standard deviation scalar value attached to it, which sort of keeps it under control. And there's also they have some they add in some normalization. Where they're using, what is it? Okay, so they're normally they have a normally there's some fancy ways of initializing your parameters, but they just do it from a normal distribution. But at runtime, they're using um, they scale the weights during training, like in a pre-specified way. Um, and the whole idea of using normalization is that it sort of ties into this idea that when you're doing these sort of advanced optimizers beyond gradient descent, like momentum-based optimizers, what they're doing is that you divide by like the norm of the gradient. So it sort of has this sort of stable. It's sort of controlling so momentum effectively. It's kind of manipulating the learning rate. And it's accounting for like the norm of the gradient as well. So by normalize, so similarly, if you normalize the generator and discriminator gradients, or generator and the discriminator, then it won't like get out of control, and it will learn more stably. And finally, they mention pixel-wise feature vector normalization. Although I don't think I'll get into that, and I probably would have to read more about that. And there's a typo here. But basically, if I remember correctly, they normalize features. Is this the same as before? But they normalize features for each pixel. For each pixel, they average out over the batch of they average over the batch of examples the normalized value for each feature. That doesn't quite sound right, but anyway, well. But the more important key is that these are all tricks to keep it stable. But the more important thing, and like maybe it won't train as stably, but it's to sort of have this sort of hierarchical structure instead, to try to like train from coarser to finer. And yeah, so that's I think I lost a little bit of energy near the end there, but so that's sort of my talk on GANs. And hopefully by the end, the idea behind this talk was to like sort of show how impressive they could be, just give you some basics, and then also just give you some like practical hands-on intuition on why they tend to fail. And also with that knowledge, like sort of have a straightforward example of how to actually build the GAN at the same time. And then after that, sort of talk about like some of the more advanced architectures, which are actually pretty not too difficult to implement, namely the DC GANs, least squares GANs, and the Wasserstein GANs. And also finally to like give a quick overview of the state-of-the-art progressive GANs, and sort of the motivation on how you would try to create it yourself. And I think that's all the time I have for now. I can look if there's any questions, and um, other than that, just I'll be looking at questions in chat, and if you are in the Western Hemisphere, then you can have a happy Easter or rest of your weekend. And thank you all for coming, and I'll be checking for questions for a little bit. Thank you. And once I figure out how to end this.